Hi guys, today we're going to learn about parametric equations, vectors, and calculus. Specifically speaking, we're going to talk about motion along the curve, okay? Some refreshers here. If a smooth curve C, okay, the curve, is given by the equations x equals f of t and y equals g of t, then the slope C at the point x comma y is going to be given by dy dx is equal to dy dt over dx dt, where dx dt is different than 0. Similarly, the second derivative is given by the derivative of the dy dx divided by dx dt. The second derivative can be used in the second derivative test for finding maximum or minimum values and for determining, obviously, concavity. Now, another notation that you need to remember that we don't make any difference between this notation and this one is this one. X prime of t is going to be equal to dx dt. Okay, we introduced this notation above, and we know that this is going to be the rate of change at which the x coordinate, okay, is changing with respect to t, or the velocity of a particle is changing in the horizontal direction. Why horizontal? Because we're talking about x. Okay. Similarly, we have that y prime of t is equal to dy dt is also introduced above, and this is going to be the rate at which the y coordinate is changing with respect to t. Okay, in other words, the velocity of a particle in the vertical direction. We are talking about vertical direction because we know that y represents the y-axis. Okay, some information here that it's connected to unit 3. Okay, we know that the position, okay, is going to be your original function. Okay, explicitly talking about the position vector, the position. Now, if we talk about the position vector, okay, or a position defined parametrically, okay, what you're going to have is that the position vector at any time t is going to be x of t comma y of t. Okay, so this is going to be your position. Similarly to what we have covered before, you know that the velocity is going to be the derivative of position. Therefore, if you have the velocity vector at any time t, then you are going to have the first component is going to be the derivative of x comma the derivative of y. Please remember something. Okay, we use this pseudo parentheses that we call them chevrons, indicating that these are vectors. Okay, similarly, the acceleration vector at any time t is going to be the second derivative of x comma the second derivative of y. Okay, so nothing too surprising here, but I just wanted to make sure that you remember this relationship. Okay, now please remember that the derivative of a parametric curve dy dx is going to be the rate of y with respect to x, or also we can talk about it as the slope of the tangent line to the curve or the slope of the path of for a particle. Okay, the second derivative, okay, which is the rate of change of the slope of the curve with respect to x, is going to be annotated like this, or we also can tell and ask you about the second derivative, right? Okay, so those are the notations that we need to revisit. The next one that we have, and the last two that we have for today, are a little bit important. Okay, so the first one is going to be the speed of the particle, okay, or the magnitude of the velocity vector. Okay, the magnitude of the velocity vector is very important. Usually speed is very important information when you are talking about, okay, parametric equations. The square root of dx dt square plus dy dt square is going to be what we call the speed of the particle or the magnitude of the velocity vector. You can also represent this as x prime of t square plus y prime of t square, everything inside the square root. That's also correct notation. Use the one that you prefer. Okay, similarly, connecting this with yesterday's lesson, what you have is that the integral from a to b of the square root of dx dt square plus dy dt square dt is going to be the arc length, okay, for a t that is between a and b, or the distance traveled by the particle for t that is between a and b. Remember, this is the arc length. Let's work this example. A particle moves in the xy plane so that at any time t, the position of the particle is given by x of t is equal to 2t power 3 minus 5t power 2, and then we have that the y of t is going to be equal to 2 times t power 4 plus t power 3. What they are giving you here is the position vector. Okay, so if you want to rewrite it, you don't need to, but here I'm showing you how to write the position vector. Okay, this is going to be your position vector, where this is your x component and this is your y component of the vector. Sorry about that. That shouldn't be a comma. That should be a plus. Okay, plus t power 3. Okay, now to find the velocity vector when t is equal to 1, what you need to do is you need to take the derivative of position. Therefore, you know that s prime of t is going to be equal to v of t, which is going to be equal, and this is a polynomial and this is also a polynomial, so you just 3 times 2 is going to be 6t power 2 minus, and then 2 times 5 is going to be negative 10t. Okay, comma, and then that's another polynomial, 8t power 3 plus 3t squared, and that's going to be your velocity vector. But that's not it. They are telling you when t is equal to 1. Therefore, what you need to do is you have that velocity, you are going to substitute the t for the 1, and then you are going to have that this is going to be equal to 6 times 1 squared minus 10 times 1, comma, 8 times 1 power 3 plus 3 times 1 power 2, which we know that this is going to be equal to negative 10, comma 11, and that's going to be your velocity vector when t is equal to 1. Please note something. Please make sure that when you label this, you have the 1 here, because v of t is not going to be equal to this. It's specifically when time is equal to 1. Okay? So now, similarly here, they are asking you about the acceleration vector when t is equal to 1. Therefore, you know that acceleration is the derivative of velocity, or in other words, the second derivative of position. So what you can do is double prime of t, or b prime of t, or just acceleration. Okay, what are you going to do? You are going to take the derivative of this polynomial that we have here, which is going to be 12t minus 10, comma, and then you have that this is going to be 24t squared minus 6t. Okay, and then you know that that's the acceleration vector. Now at t equals 1, you are going to replace the t for the 1, so you have a of 1 is going to be equal to 12 times 1 minus 10, comma, 24 times 1 squared plus 6 times 1, which we know that this is going to be equal to positive 2 and positive 30, and that's going to be your acceleration vector when t is equal to 1. Isn't that nice? So please remember, we're going to use the same properties that we have in law from particle motion. Okay, so that's the reality, and that's always going to be the application of this situation. Okay, so now let's answer some of the questions here. How do you find the magnitude or the length of the vector? So your position vector is going to be this one. Okay, let's say that that's your position vector. Okay, so what you know here is that your x component of the position vector, okay, is going to be, well, x of t. Okay, and then you know that your y component of the position vector is going to be y of t. Okay, therefore the magnitude of the position vector is going to be the square root of x of t squared, okay, plus y of t squared. All of this inside the square root. That's going to be the magnitude, okay, of the position vector. They are not going to ask you this. It's not very common to be asked for this, but it's an FYI. Now, the one that is very popular is the magnitude of the velocity vector. You know that the velocity vector, it's formed by the derivative of the x component. Okay, so this is going to be formed by x prime of t, not x, and this one is going to be formed by y prime of t. Okay, y prime of t, and you know that that's a right angle. Okay, so the magnitude of the velocity vector, we know, following the same idea and the definition from physics, you know that it's going to be x prime of t squared plus y prime of t squared, and you know that this also comes from the idea of the distance formula. Okay, so you also know that if you want to have the geometrical meaning as well. Okay, so please note that this is something very important. Why? Because the magnitude of the velocity vector is what we call speed of the object moving along the line. So this one, okay, is very important for applications, and you are going to find that a lot of textbooks, exams and courses, they use this one a lot. Okay, that is very popular when you have tests applications, everything. Okay, so obviously this is very popular because of its applications. Okay, similarly, the acceleration vector, you know that it's going to be formed by the second derivative of position, okay, the x component of position, and the y component is going to be the second derivative of the y. Okay, so similarly, the magnitude is going to be the square root of x double prime of t square plus y double prime of t square, and everything inside the square root. Okay, and that's going to be the magnitude of the acceleration vector. Okay, so we have here all the magnitudes. You can see that this, in case that you are wondering, okay, the position vector, this is going to be the vector s, this is going to be the vector v, and this is going to be the vector acceleration. Okay, so in case that you are wondering about the notation. Okay, so let's do this example so you can see that it's pretty straightforward to apply these formulas. Okay, so here in the example you have a particle that moves in the xy plane, so that at any time where t is greater than 0, greater or equal than 0, the position of the particle is given by the x component is t squared plus 5t, and the y component is natural log of t squared plus 4. They are asking you to find the magnitude of the velocity vector when t is equal to 3. Okay, so first of all, that is going to be the position vector, so you want the velocity vector. For the velocity vector, you know that I need to find the derivative of the x component, which you know that it's a polynomial. So it's going to be 2t plus 5, and then the derivative of the y component, what's going to be that one? You know that it's going to be 1 over t squared plus 4 times 2t. Okay, and as you can see, I just knew that about the chain rule, so that's why I didn't even put the 1. Okay, I just did the multiplication there. So technically speaking, these are the two components, okay, of the velocity vector. Therefore, what are you going to do? You know that the speed, okay, or the magnitude of the velocity vector when t equals 3, okay, I'm going to put it here, speed at t equals, what's that, 3, is going to be equal to what? You have that it's going to be 2t plus 5 square plus, and then you have that it's going to be 2t divided by t squared plus 4, and everything square. Okay, everything inside the square root. Okay, but you know that that's not it, because we need to evaluate this at t equals 3, and that's why I'm indicating here that I'm going to evaluate at 3. So what are you going to do here? Well, you're going to plug the 3 instead of the t. Okay, so you have something like this, square plus, and then you have 2 times 3 divided by 3 squared plus 4, and all of this in parentheses, and then I'm going to put another parenthesis, square. Okay, so that's what we have. If you want to simplify it a little bit more, you can leave it like that, right? Or this one, you know that it's going to be 11 square plus, and this is going to be, what's that, 6 over 13 square, which is not a very nice number, so I would leave it like that. Okay, and that's how you can find the speed. Okay, so that's for this example. Isn't that simple? So don't complicate your life, you don't need to simplify it. So let's look at the next example. Okay, in this example they are asking you about a particle that moves in the xy plane, so that x is equal to root 3 minus 4 cosine of t, and y is equal to 1 minus 2 sine of t, where the t is in between 0 and 2 pi. Okay, this is recalling the unit circle. You have sine and cosine. The path of the particle intersects at the x-axis twice. Okay, so what is intersecting at the x-axis? You know that a line intersects the x-axis when y equals 0. Okay, so they are asking you, write the expression that represents the distance traveled by the particle between the two y-intercepts. Okay, so they are telling you that there's two y-intercepts. Okay, and in addition to that, you know that we need to find where this intersects the x-axis. Okay, so as I was telling you, we know that we know that there's a x intercept, okay, when y equals 0. Okay, now ask yourself, do you see a y? Yes, I see a y, this. Okay, so what you're going to do here is you're going to let your y be equal to 0. So you let this expression to be equal to 0, the y component. Now ask yourself, can we solve this via precalculus or precalculus knowledge? Absolutely. Okay, what are you going to do? You're going to move the sign to the other side, so you have 2 sine of t is going to be equal to 1, and then divide both sides by 2, so you have sine of t is going to be equal to 1/2, and boom. What happens here? Remember that you have the restriction that the t is only between 0 and 2 pi, including the extremes. So you're like, oh, that's the unit circle. When this happens in the unit circle, you know that that happens in pi over 6 and 5 pi over 6. And we're happy people. Why? Because this is consistent with the information that they gave you. They told you that there were 2 y-intercepts, and indeed you found them both. Okay? Now let's attack the question. Write the expression, okay, so you don't need to solve it, that represents the distance traveled by the particle between the 2 intercepts, the 2 x-intercepts, excuse me. Okay, so you know that the distance, okay, or the arc length, okay, is going to be equal to what? The integral from pi over 6 to 5 pi over 6, that's why you found them. And that then you are going to have that it's going to be the square root of dx dt. Okay, now ask yourself, can we find dx dt? Yes, we can. Okay, because what we're going to do here, let me express it here so you know what we are finding. We want also the derivative of the y component, right? Now ask yourself, can we find those two? And you cannot leave it like that. Why? Because you haven't shown the reader what the derivative of the x component and the y component are. So this is what we need to find. Can you find them? Absolutely. Here I'm going to rewrite my integral, and that's the expression that they want. Okay, so you take the derivative of root 3, that's 0, and then the derivative of negative 4 cos t is going to be 4 sine t square plus, and then ask yourself, what is the derivative of 1, 0 minus 2 sine of t? That's going to be negative 2 cos t. Okay, all of this square, and then you can leave it like that. Okay, once you put the square root there and the dt, and that is the expression that they were looking for. Okay, isn't that nice? So you can see that sometimes the questions, they look a little bit funky, but the reality is that they are not that bad. Okay, put all the pieces of the puzzle together and you should be fine. Okay, so let's look at the next example. We learned earlier in the year, okay, that a particle moving along the line is at rest when the velocity is 0. And back in the day, when we have like an explicit function, it was easier because you just set the equation equal to 0 and you solve it. But here the issue is that we have vectors, right? So if a particle is moving along a curve, the particle at rest needs to be at the vector 0, meaning both components need to be 0 at the same time. Please note something, at the same time, okay? You are going to see that it's not that bad, but you need to be a little bit careful. In the AP test, this question is very common in the multiple choice. Okay, so let's read this one so you can see that it's simple. A particle, again, moves in the xy plane so that at any time t, the position of the particle is given by 2t power 3 minus 15t squared plus 36t plus 5. And the y component is t power 3 minus 3 t power 2 plus 1, where t is greater or equal than 0. You know that that's an application problem, so it makes sense. For what values of t is the particle at rest? So what are you going to do? As I'm always telling you, when in doubt, take the derivative. So you take the derivative of the x component, okay? And you're all happy because this is a polynomial, so 6t squared minus 30t plus 36. Do you agree with that? Now, what you're going to do, because you want the particle at rest, you want the x component to be equal to 0. So you're going to set this equation equal to 0. Now you're going to be like, well, that leading coefficient is 6. Well, yes, but you can factor that out. So you have 6t squared minus, and you have that this is going to be 5t plus 6 is going to be equal to 0. Then ask yourself, is this quadratic something user-friendly to factor? And the answer is yes. You can see that it's going to be t minus 2, t minus 3 is equal to 0. Therefore, your two t values are 2 and positive 3, which both are within the restrictions that we have. So at this point, we're like suspicious. We don't know exactly where, but we have two candidates. Okay, now what are you going to do? After that, you are going to take the derivative of the y component, okay, on this side. So you have the derivative of the y component. What's going to be that? That's another polynomial, so very user-friendly. So you have 3t squared, okay, then minus 6t is going to be equal to 0 because the derivative of the 1 is 0. So again, you can factor this equation because you are equalizing to this component. So you have that it's 3t parentheses, and then you have that it's going to be t minus 2 is equal to 0. Now you have that the two factors are going to be 0 and 2, okay, which both are within the restrictions of the t, but you recognize which one are we going to pick. Are we going to pick 0, 2, and 3? No. Okay, the two that are matching is the value t equals 2. So thus, what you have here is that the particle, okay, the particle is at rest, okay, at t equals 2. Are we okay with that? Why not t equals 3? Because t equals 3, only the x component is 0. Okay, the other one is not going to be 0, and vice versa with the 0. Do you see it? So we only have one time where the particle is at rest in this equation. Okay, so let's look at another type of question that is very popular that I really like. Okay, so this one. A particle moves again in the xy plane such that a way that its velocity vector is this one. Please note that this is velocity. Okay, so I'm going to put it there. At t equals 0, the position of the particle, okay, so the position is 7, negative 4. Find the position at t equals 1. Okay, so this is screaming use the fundamental theorem of calculus. Okay, why? Because they are giving you velocity. You know that velocity is the derivative, okay, of position, and they are asking about position. So what are they asking? You need to have that x prime of t, okay, the derivative of x, okay, is going to be equal to 3t squared minus 4, and that we are getting this from the hypothesis of the problem, okay, because that's velocity. They are defining that. So you're like, how in the world I can find the integral, okay, evaluated at, well, not the integral, but x prime of 1, okay? So this will use FTC. So we know that by FTC, what do you have? The integral of, okay, x prime of t dt, okay, is going to be equal to the bounds, okay, of your integral. And what are those bounds? They are giving you the value at 0, okay, which is this one, okay, because we're in the x part, okay, so you know that I want 0, and they are asking for 1, so they are asking for 1 and 0. Are we okay with that? So by fundamental theorem of calculus, I know what I want and what they gave me, so that's why I have the x of 1 minus x of 0, okay? So what are we going to do? We're going to take the derivative of this guy. You know that, not the derivative, the integral of this guy. Okay. So what's next? Next, you are going to take the integral, okay, which is going to be t power 3, okay, minus 2t squared, okay, and you're going to evaluate that from 0 and 1, okay. Yes. And then you know that you are looking for x of 1. And then you have that x of 0 is going to be the 7 that we have here, okay. Then you plug the 1. What do you have when you plug the 1? You have that this is going to be negative 1, okay. It's going to be equal to x of 1 minus 7. Do you see it? Therefore, what do you have here? You have that x of 1 is going to be equal to, pass that 7 positive to the other side, so you have that it's 6, so that's going to be the x of 1. Now you have the x component, but you need to do the same thing for the y component. So what are you going to do? You are going to identify that y prime of t is going to be equal to 8t cubed plus 5, and now you are going to use again fundamental theorem of calculus. Okay, so you have that you need to use the integral from 0 to 1, y0 and 1, because those are the ones that you also have for the y component, okay, so y prime of t dt is going to be equal to y of 1 minus y of 0. Okay, how does this change? Because instead of taking this value, I'm going to take this one. Okay, so you are going to integrate this. Okay, so you know that integral, the integral of 8 t power 3, that's going to be what? 2 t power 4, okay, plus 5t, okay, and we're going to evaluate this from 0 and 1, and that's going to be equal to y of 1 minus 4, so plus 4. Okay, so now, okay, you are going to, and let me do a line here, you are going to plug the 1, therefore what do you have here? We have, when we plug the 1 here, you have that's going to be 7, the 0, it's a 0, so I just leave it like that, y of 1 plus 4, and then what do you have here? You have that y of 1 is going to be equal to 7 minus 4, which is going to be equal to 3. Okay, therefore what do you have here? You have thus, okay, the position, always go back to the question that they're asking, the position, okay, of the particle, okay, at t equals 1 is going to be, okay, 6,3. Okay, so they are not asking about is it a vector or not, so I'm just going to leave it as a point in this situation. Okay, and that's it for today. So I hope that you find this video helpful. Bye.